Hi, everyone. My name is Tom Burkhead. I'm one of the second-year fellows in infectious diseases at University of South Florida. Today, I'll be talking a little bit about a brief history of vaccination. Today, the objective is really just to summarize a few of the significant events in vaccine history and the scientific advancements that have really shaped our understanding and use of vaccines today. Today's not necessarily an exhaustive review of vaccinology, the current guidelines on adult immunization, or some of the social issues around vaccination, although there are some other good talks in the podcast series about vaccine hesitancy, adult immunization, and several of these other topics that I encourage you to look at as well. And as a disclosure, I have no financial disclosures. So moving on, some of the earliest beginnings of vaccination were with a process that we refer to today as variolation, which was done, we know, in the mid-1500s and possibly much earlier than that as well. But the ancient Chinese were some of the first to do this process. And what it involves is taking components of infectious material from someone who had the disease, who had smallpox disease, and introducing it into a healthy host. Typically, this would be scabs that would be inoculated into the skin or the nose that would cause a milder disease, but that would then induce immunity against vaccination, or against the disease if someone was exposed to the disease later on. There was the Silk Road of trade routes that eventually led to the spread of this practice from China and the Far East to other parts of the world too, including Europe. And one of the notable people around this time was a woman named Lady Mary Montagu. She was a very prominent member of British society. She was a very outspoken writer and social critic. Her brother actually died from smallpox. And as a child, she was also afflicted with the disease. She was known to be very beautiful, but with the disease she had, she was fairly disfigured from it, also left without eyelashes. Her husband actually served as an ambassador from England to the Ottoman Empire, leading her to Constantinople in what we refer to today as Istanbul, Turkey. And while she was traveling there, she noticed that the people there had this astonishingly clear skin because they were not afflicted with smallpox as heavily, and she began to realize that this was tied to their practice of variolation. And this prompted her to become a big advocate of it. She actually had it performed publicly on her daughter after she returned to England. One of the famous experiments at this time was called the Newgate Prison Experiment of 1721, where 6 prisoners were offered freedom if they agreed to try variolation. Were later exposed to smallpox and survived. All 6 went through with that experiment and were freed, which really started to draw broader attention to the practice. And then variolation, it eventually became much broader practice throughout England. Of course, although for its advantages, it had many skeptics and definitely some costs associated with it as well. There was just, of course, the preparatory and recovery periods involved, the costs of doing the process itself, and the time involved. The mortality, 2 to 3% of those variolated actually died in comparison with 20 to 30% who actually died after contracting smallpox. So, of course, it's still a tenfold decrease, but there was a very real risk of having no serious disease with variolation too. This also happened to a son of King George III at the time. It was also transmissible to others during that recovery period. Some accused physicians of advocating for it for profit as well. In the New World, smallpox epidemics took a toll there as well, in Boston, New York, and Philadelphia in the 1700s. Ben Franklin actually became a big advocate of variolation during an outbreak in the 1750s when he found a very favorable mortality benefit. And George Washington actually mandated that inoculation occur against smallpox for the Continental Army recruits in what many consider the first mass immunization of a military power, or the first vaccine mandate. The name many of us have heard before is Edward Jenner, who tested the hypothesis that infection from cowpox could protect a person from smallpox. He had noticed that the milkmaids who contracted cowpox after working with cows seemed to have this protective benefit against smallpox when they were exposed later. And what he did, he actually inoculated an 8-year-old boy, James Phipps, who was the son of a gardener, with cowpox from the hands of the milkmaid. James had a local reaction, but he fully recovered and was subsequently protected against smallpox. This today is one of the most famous experiments in vaccine history. And that main reason being it was the first scientific study of an attenuated form of an infectious agent to protect against the human pathogen. One interesting point to note, vacca is Latin for cow, providing the stem in vaccinia and later vaccine, which wasn't a term that came to be used for many years after that. What is interesting to consider at this time is notable is that event was the scientific reason for it was not well understood at all, and wouldn't be for many years. Many diseases at the time were thought to be due to physical and chemical transformations of tissues, with microbes being incidental findings. Some thought disease was due to miasma or bad air. Spontaneous generation was a prevailing theory on the generation of new life at that time from decaying matter. Then the mid to late 1800s were a time when there was a tremendous growth of new knowledge and understanding that was really paved by new advances in microscopy and microbiology, and several notable individuals, including Pasteur, Cook, Virchow, and several others who I'll talk about. One of the interesting stories from this time is from Vienna, Austria. The physician, Dr. Semmelweis, was a faculty member in the obstetrics unit at this hospital. And he had noticed that childbed fever, as they referred to it at the time, which we now know as streptococcal disease, it caused the death of about 1 out of every 10 mothers at the time. So a very significant cause of mortality. He had noticed that there was an association between the odor from the women dying and that from the corpses studied by the medical students and faculty, who were, of course, going back and forth between the two at a time when hand washing and sanitation wasn't a common practice. And he hypothesized that there was a putrid matter, as he called it, that was actually transferred on the hands of the physicians and students, and was possibly a cause of this condition. 1847, he used a chlorinated lime solution and had the students and faculty use this in between patients. And that year, there was actually a 4-fold decrease in mortality. Despite that, his contributions really weren't understood for many years later. But some other important people are Leeuwenhoek, who we know of for his work with microscopy. There was John Snow, who many consider to have done the first epidemiological study with cholera outbreaks in the 1840s and 50s in London, he actually traced many of these cases back to the water source as being the vector for disease. There's an iconic photo of a water pump in London that's a tribute for him in his studies at the time. Louis Pasteur was the founder of germ theory. He debunked spontaneous generation, developed the process of pasteurization, and was integral to some of the first widely used vaccines in animals and humans. Virchow was the founder of cellular pathology and cell theory, the idea that organisms are the structural unit of organisms is cells. Of course, Robert Koch, his postulates that are used as criteria to establish whether a particular microbe is the cause of disease. So a little more on Pasteur. He's arguably one of the most influential people in the history of vaccination. He after variolation, he pioneered a lot of efforts to develop some other vaccines. He actually coined the word vaccination as a tribute to Jenner in the late 1800s. Some of his first work was with chicken cholera, which was caused by Pasteurella multocidum. He exposed some chickens to 1-month-old cultures of the organism. And when the same chickens were exposed to a fully virulent strain, they survived the challenge. This is this is credited with saving much of the chicken industry in Europe at the time. Some of his efforts progressed into work with anthrax vaccination. Historically, anthrax in humans is always depended on control of the disease in livestock as well. And some early observations found that the cows inoculated with pus from other cows demonstrated a protective effect, very similar to variolation. And this is kind of what's prompted interest in doing similar practice for vaccination in animals and humans. There's a veterinarian who subjected sheep's blood to elevated temperatures, 55 degrees C for 10 minutes prior to challenging healthy sheep with an attenuated version of the pathogen, much as Pasteur had done with chicken cholera. Pasteur adopted this approach and found that growth at slightly lower temperature could happen without spore formation, and then it could show progressively less virulence the longer it was incubated. So at 8 days, it was less virulent for rabbits and sheep. Over a 6-week period, it eventually failed to even kill mice and guinea pigs. Another famous experiment happened in a little town just southeast of Paris at the farm of a veterinarian who was actually set out to disprove Pasteur's germ theory. Important context to know at this time, Pasteur was, of course, trained as a laboratory chemist and was not formally medically trained. And that really prompted a lot of mistrust among the medical community as far as some of his observations and suggestions. They called him a conceited laboratory chemist, unversed in medical thinking. But this is really so this is important context to know when this experiment happened in 1881 at the farm of this veterinarian. He actually vaccinated 24 sheep, a goat, and 6 cows with the 2-dose series of anthrax, with, of course, attenuated versions of the pathogen. And then he also used a similar number of controls. He found that when challenged with anthrax, almost all the animals without the vaccine died, whereas those who had the vaccine survived. And this actually created a huge amount of media, press, and attention at the time, and really publicized a lot of his observations and his work. Some some of Pasteur's important work was also with the rabies vaccination. Rabies at the time was invariably fatal, but very poorly understood beyond its transmission through infected saliva. Pasteur showed that transmission between rabbits could also occur through inoculation of the nervous system tissues. And this really kind of demonstrated that the causal agent was not only found in saliva. And he also realized that this shortened the incubation period. He also found that if he did the same, but allowed the virus to air dry, then it would become progressively less virulent. And then after 15 days, it was actually no longer virulent at all. So in an experiment that is reminiscent of Jenner's variolation, his cowpox experiment was done with rabies vaccination. There was a 9-year-old boy, Joseph Meister, who experienced a severe bite from a rabid dog. And Pasteur, along with a pediatrician, administered a vaccination series to the boy. They started 60 hours after the bites. He was inoculated over the abdomen with a 15-day-old desiccated spinal cord specimen from an infected rabbit. And then he progressed to do 12 total inoculations over the next 10 days, each with a more virulent virus. And Joseph Meister survived despite his bites. And this was the first successful evidence of therapeutic administration of a vaccine. We refer to that today more so as post-exposure prophylaxis. But this was the first time that was really shown to work. And Joseph Meister actually grew up to be a security guard at the Pasteur Institute later in life. So another important thing to know at this time was the development of human immunology as a distinct discipline, which developed in the late 19th century, of course, with theories of cell-mediated and humoral immunity. In 1884, there was a Ukrainian scientist named Mechnikov who observed phagocytosis in starfish and hypothesized that the same process would occur in higher species as well. He eventually received the 1908 Nobel Prize for that. There were a couple of German physicians, notably Behring, recognized that serum factors prevented lethality from bacterial toxins, notably with tetanus and diphtheria. These antitoxins, they were later discovered to be antibodies, and that they could be passively shared from one person to the next, which has to deal more with passive immunity that I'll talk more about in a bit as well. Of course, thinking about the immune system, we have our innate and adaptive immunity. Innate immunity being the non-specific mechanisms by which the body protects itself from pathogens. The skin and stomach acid being important barriers. We also have macrophages, natural killer cells, form phagocytosis, along with the complement system. The adaptive immunity is what's more so associated with the immune response to vaccination and protection through vaccination. Developed, of course, later in evolution to provide immunologic memory, both through humoral and cell-mediated mechanisms. And of course, the immune system is a talk in and of its own. Another development at this time, up to this point, most vaccines were derived from a naturally occurring pathogen or an attenuated version, such as with vaccinia, anthrax, rabies. The late 19th century introduced the idea of inactivation of bacterial pathogens in human vaccination. There was, in 1886, Theobald Smith and his chief, Daniel Selman, developed the first successful heat-killed vaccine against the agent of hog cholera. Inactivation was subsequently applied to human vaccines for typhoid, plague, and cholera, each of which have an interesting story. Cholera was notable as one of the first attempts to induce immunity in humans to a bacterial pathogen. Waldemar Hefkheim was a Ukrainian-born scientist whose efforts with vaccine against cholera became very famous, primarily related to his trials in India with the vaccine. These are widely considered to be some of the first human vaccine trials. With cholera in the late 1800s, he vaccinated over 40,000 individuals against cholera with with very successful results. And shortly thereafter, developments toward a heat inactivating, whole cell cholera vaccine. It was easier to prepare. Also showed a lot of promise and success, over 80% effective in studies at the time. And modifications of the killed cholera vaccine formed the foundation for that vaccine throughout much of the 1900s. There's a variety of them were given in the middle of the century, including to Allied troops who were stationed in regions where cholera was endemic, which is attributed to greatly decreasing the incidence of disease among the troops. Today, we use a live oral vaccine for cholera in the United States for travelers in areas where there is active transmission. Killed varieties are also in widespread use outside the U.S. Typhoid vaccination, live vaccination with typhoid was originally attempted in the late 1800s as well. Wilhelm Kohl later used heat-killed typhoid vaccine in animal models prior to be used in humans. In the early 1800s, efforts to immunize troops with an oral form by James Carroll, who previously studied yellow fever, kind of paved the way for its use in subsequent years. World War I, use of a typhoid vaccination was thought to greatly reduce the incidence of disease as compared with the Spanish-American War a few years before. Today, we still use both live and inactivated typhoid vaccinations. There's a live oral vaccine, as well as a parenteral vaccination. And none are completely effective, but they are still highly efficacious, safe, and recommended for travelers to areas with high risk of exposure. I touched briefly on the idea of passive immunization, and just returning to this idea, because we have active and passive immunization. Active immunization is more so what we associate with vaccination, wherein the body develops an immunologic memory to a weakened form of the pathogen. Passive immunization is distinguished in that the protection is through an exogenously produced antibody. We're familiar with this in terms of transplacental transfer of antibodies from a mother to a fetus that provide protection for the first 3 to 6 months of life. And this is really what formed the basis for using the protective effects of antitoxins for tetanus and diphtheria as well. What they refer to as serum therapy. Behring also did some key work in this area. He discovered that serum from animals who had received sublethal doses of both tetanus and diphtheria could be injected into other animals and create a protective effect. This was initially called passive transfer, eventually leading to serum therapy. And what's notable about this led to the inaugural Nobel Prize in 1901. That was for the discovery of serum therapy. Large-scale production of this followed shortly thereafter, and the efforts to standardize that, standardize these methods led to some of the first standard reference preparations that humans began to use. And one of the early incidents associated with the antitoxin solution It was in 1901, several children died in St. Louis when one of the solutions was contaminated with tetanus spores. This really prompted some of the first regulation, including the Biologics Control Act, which was the first law implementing federal regulations of biological products, including vaccines in the U.S. Shortly thereafter, we had the Pure Food and Drug Act in 1906, and these developments eventually led to the Food and Drug Administration that we know of today. And I'll circle back on that a little bit in a minute. Moving along in history, in addition to serum therapy, the efforts towards vaccination for diphtheria and tetanus occurred largely in parallel too. The first tetanus toxoid vaccine was licensed in 1926 and subsequently diphtheria in 1933. Variations are still used, of course, today. We know of the Tdap, DT, DTaP vaccinations. What was really notable about these vaccines is that it was discovered that by conjugating these toxoids with an aluminum salt adjuvant, you could greatly improve the immune response by conjugating that adjuvant, to the protein itself. Studies demonstrated that you had a far stronger immune response in doing so. Tetanus and diphtheria, these are among the first vaccines to do this. Just looking at the mortality and incidence of tetanus in the U.S., as we all know, it declined greatly with early 20th century, seeing a dramatic decline. And of course, the widespread immunization of troops in World War II led to significant reductions in death due to tetanus as compared with World War I. For a little modern day context of adjuvants, they're a very critical component of many of the vaccines we use today, including meningococcus, pneumococcus, influenza. Of course, in we talked about tetanus and diphtheria, HPV and hepatitis A and B vaccines, all the way up, including some more experimental vaccines today. These can cause some more localized reactions because of that stronger immune response with some localized pain, swelling, and redness at the site of injection. So for that reason, of course, one of the most widespread vaccinations today, influenza, it had its beginnings in the early 1940s. Thomas Francis, Jonas Salk, who we know of for his work with polio, and I'll talk about that shortly. They were lead researchers at the University of Michigan to develop the first inactivated flu vaccine with the U.S. Army. A lot of this was inspired by the 1918 pandemic and the loss of troops during World War I. They utilized fertilized chicken eggs in a manner that's still used to produce many of our flu vaccines today. In 1945, the first inactivated influenza vaccine was licensed. And what was interesting, it did not take much time at all to realize that the antigenic changes of the influenza virus year over year would be important or would lead to us, modifying the vaccination on a yearly basis, based on the antigenic changes from year to year. One of the most possibly well-known stories, and I think in vaccination in history, is with polio. Polio really struck a lot of fear into the public. It really presented without warning in many cases, and of course there was no cure. CNS involvement was not a pervasive adverse effect of all cases, but of course it did affect many. And this is one of the interesting times when better hygiene actually it led to fewer exposures as infants when infection is milder. the maternal antibodies offered some protection. So this is actually a time when we had increased vulnerability later in life because these hygiene practices actually led to less exposure early in life when the disease was milder. FDR, of course, popularized polio after he contracted the disease in the 1920s, and his efforts led to the March of Dimes, which is one of the most pivotal funding sources for vaccine research in the era. This is when the concept of the poster child, the telethons, celebrity fundraising, that's really when a lot of this was first born. Looking at just a quick timeline of the history of polio vaccination, it's really first isolated in the early 1900s. Albert Sabin showed that poliovirus could be cultured in nervous tissue. Of course, I'll talk more about him and his work with the live vaccine. In the 30s, a couple of vaccine trials were actually unsuccessful, and that's possibly a lesser known fact that there were some unsuccessful trials prior to the more famous trials with Sabin and Salk. There were some notable advances in the 40s that enabled polio virus to be cultured much more effectively, and those were really critical developments for the future studies in polio vaccination. That also, a group of scientists led to their winning of the 1954 Nobel Prize. Sabin and Salk quickly became quick rivals in the vaccine race, and they were each awarded over $100,000 for funding in 1950 to develop this. 1952 was a record year for polio, which was really prompting public support and attention to this vaccine race. And it was in 1955 that the results of the Salk's vaccine trial were actually announced. A little more about Salk and Sabin. So Salk, as I mentioned, he trained under epidemiologist Thomas Francis, first with the influenza vaccine. And his training there was really a strong influence on him and his focus on the killed virus approach. And he pursued this really at the criticism of many who felt like a live vaccine was going to be the more effective approach. But nonetheless, he was very dedicated to the killed virus approach. And he actually, early 1950s, he injected himself, his wife, and their 3 sons with the vaccine. Of course, our sequence of trials and ethics regarding trials have all changed quite a bit since this time. But it was standard practice for a lot of history for scientists to self-inject themselves and family in their early studies. In 1954, he went on to do a randomized double-blind trial of over 1.3 million with excellent efficacy. And it was in April of 1955 that his results were announced at a press conference to much acclaim. One of the public confidence was the public opinion was, of course, wildly favorable towards vaccination when this was announced. One of the events that happened shortly thereafter, there was a first grader in Idaho who contracted polio after an injection of the vaccine and later died 3 days later. There were several other cases that arose around the country. And what had happened was, in anticipation of this announcement, several companies had actually already started to stockpile the vaccine. And one of those companies was having some difficulty in producing a fully inactivated virus. The lots were discarded that they had identified, but under the regulations, there was no obligation to report a lot of those findings to the public. And it turned out that some of that lot had actually gotten out into the public. And so there was a short period of panic there while the investigations ensued. But once it was identified what the source was, the public support was quickly regained after it became clear what had happened. But over 200 cases were attributed to that accident early on. The other critical figure was Albert Sabin, who was equally a proponent of the live vaccine approach. His thinking was that this would be a much more durable response, that it would produce higher antibody levels. It was thought to be more consistent with the pathophysiologic mechanisms of infection too, through the GI tract. And he claimed that anything else was a dangerous use of time and money. At this time, there were really 3 strains of polio that had been identified in the public. And therefore, developing a live vaccine against all 3 was a much more time-intensive process to do that, which is one of the reasons his vaccine came into use at a much later time. He did much of his trials in the Soviet Union, actually, where a double-blinded model was not as widely used in favor of what they called humanitarian testing, which was essentially widespread administration of this vaccine. There was no placebos or control groups at the time, but despite that, his trials were wildly successful. He was largely credited with eliminating polio in the Soviet Union. As vaccination evolved, of course, Salk's vaccine came into widespread use first, as it was announced first. But Sabin's vaccine, it did have a number of advantages. There was oral administration as opposed to injection. There's no need for boosters. I mentioned the pathophys, more similar to natural infection and a faster immune response. And this is really what led to its use, I think, more from a public health perspective. In more resource-poor conditions, it was much easier to administer an oral vaccine in those settings too. Of course, the primary drawback, there was a very extremely rare but very real possibility of infection from the live vaccination. It was only about 1 in a million, but because of that reason, the World Health Organization urged polio-free nations to phase out the oral vaccine due to the possibility of introducing new infections in polio-free nations, because there's actually the possibility of reintroducing the disease for that reason. So, moving ahead a bit in history, we have measles, mumps, and rubella vaccination. Measles was one of the most contagious diseases in human beings. Transmission of up to 90% of close contacts. At the time period, it was considered ubiquitous and affected nearly every person by adolescence. We would have major outbreaks every 2 to 3 years, peak incidence in the late winter and spring. Development of a vaccine, it began in the 1950s with an outbreak in a Boston school where they obtained some of the specimens that were actually used in culture, culture through human kidney cells. This eventually led to an inactive virus that was later licensed in 1963. Several years later, there was the mumps vaccine in 1968 and rubella in 1969. Then in 71, the U.S. government licensed Merck's trivalent vaccine against measles, mumps, and rubella as a live virus vaccination. What's critical about this period is the idea of combination vaccines. So the ability to get a vaccination for multiple diseases in one injection became very popular just due to the need for reduced injections, reduced shipping and storage costs, overall higher vaccination rates due to needing fewer injections. As a side note, more recently we have the MMRV vaccination, which adds varicella to that protection as of 2005. To this point, most vaccines were, relying on these inactivated vaccines, but there's a new concept of polysaccharide vaccines, whereby the polysaccharide component could actually induce a immune response, became more popular. Most people consider this area after MMR to be golden age of vaccine development, with renewed interest in vaccination against pneumococcus in particular. The interest in a vaccine against streptococcal disease started earlier in the 1900s, due to the association with otitis media, meningitis, respiratory infections from streptococcus pneumoniae. But interest, of course, waned with the advent of penicillin and antibiotics. Then it, of course, did become, the interest arose more later on to explore a vaccine against strep pneumo. As I mentioned, the prevailing theory was that proteins are superior immunogens, although early work in the 1800s did show immunogenicity to polysaccharides. Robert Austrian was a researcher at the University of Pennsylvania School of Medicine and published data showing the persistent mortality of the disease despite antibiotic therapy, which was a big part of renewing interest in the vaccine. He dedicated much of his life to developing this vaccine. Some of his trials were in South Africa, in gold mines, where the workers there would come for 6 to 9 months at a time. Of course, these individuals were immunologically naive to that environment, and there would be very large outbreaks among groups when they were exposed. His trials using pneumococcal vaccination in that group showed over 80% reduction in the incidence of pneumococcal pneumonia. So some extremely successful results. In 1977, the first pneumococcal vaccine was licensed. It was active against 14 strains. In 1983, the second pneumococcal vaccine supplanted the original, active against 23 strains, which we know as the Pneumovax 23, still in use today. Of course, the 70s and 80s, that eventually led to use of purified bacterial polysaccharide components for vaccines against pneumococcus, meningococcus, and also H flu type B. See, as far as pneumococcal conjugate vaccines that came about later, some subsequent studies showed that conjugating that polysaccharide to carrier protein actually introduced a stronger immune response. And then in 2000, the first pneumococcal conjugate vaccine was licensed in the U.S. as the Prevnar 7. 2010, we had the 13-valent version, which is still widely used today. Some studies exploring some vaccines against even more strains that are ongoing. An important development around this time was the idea of recombinant vaccines. Some initial trials with the hepatitis B vaccine focused on the Australia antigen, they called it, which was later found to be the hepatitis B surface antigen. The hepatitis B vaccination was really the first to use this idea of recombinant technology, wherein you could actually splice a piece of DNA into another cell and culture to actually produce an antigen at large scale. And hepatitis B was one of the first vaccines to use this technology, and that's been applied in hepatitis B vaccination since 1986. Another development around this time was the idea of vaccine as a tool to prevent cancer. Hepatitis B was really more so the first one that could have a benefit in reducing cancer, namely liver cancer. Although possibly the human papillomavirus vaccination is what we more famously associate with that. And it was noticed, even in the mid 1800s, that there were some, demographic variations in uterine cancer. There was an Italian pathologist who noticed that uterine cancer was predominantly one of married women rather than single women and nuns. And that it also tended to happen in younger women. It wasn't until the 70s that the new technology actually enabled us to understand, why that was. When, we realized that human papillomavirus was a common cause of both warts and cervical cancer. Specifically, types 16 and 18 were strongly associated with anogenital and tonsillar cancers. It was found that working with some of the structural proteins, even low levels of protein expression could lead to the assembly of what they call virus-like particles that could induce protective immunity. Initially, it was much more difficult to find a component of virus that would induce an immunologic memory, but the discovery of these VLPs that could do so kind of paved the way for the development of a vaccine. Using those similar recombinant techniques that were used for the hepatitis B vaccination, we had a way to produce these particles at large scale. Eventually, this led to quadrivalent vaccine for types 6, 11, 16, and 18, which was known as Gardasil. A bivalent vaccine came out shortly thereafter, although it's no longer in widespread use due to having vaccinations that are active against more strains of the virus. Currently, only the 9-valent vaccine is available in the U.S., active against a number of strains presented there. And there's a wealth of data about the benefits and the positive impact of this vaccine on reducing human disease. And within 4 years, there was one study in particular that showed that the vaccine type prevalence of HPV decreased greater than 50% among teenage females, despite only about a third in the study completing the full 3-dose series, which a lot of this is that decline is attributed to just the widespread development of immunity that protects even those who aren't vaccinated from being exposed as well. Another important technology is adenovirus-based vaccines, which are another form of recombinant technology. Adenoviruses, what they are non-enveloped double-stranded DNA viruses that cause mild respiratory and GI tract infections. What drew our attention to the use of these vaccines, or the use of these viruses as a method for vaccination, they have a very well-characterized genome. They're easily manipulated, and they can be modified in the lab to be they call a replication defective virus, so unable to replicate once they're introduced into a host. And that's made them very attractive for vaccines and cancer gene therapy as well. They have a broad tissue tropism that allows them to target a range of dividing and non-dividing cells. They have very high thermal stability and are highly immunogenic as well. There have been human clinical trials for adenovirus-based vaccines and for HIV, Ebola, influenza, and a number of others as well. Possibly most famously, we associate these in current times with vaccination for SARS-CoV-2. Of course, three well-known vaccines in widespread use for COVID-2 based on the adenovirus platform. The AstraZeneca vaccine, of course, the Sputnik vaccine, developed in Russia, the Johnson & Johnson vaccine, used widely in the U.S. And of course, with COVID-19 vaccination, we also know of the mRNA vaccines. mRNA was really first described in the 1960s, shortly after we discovered DNA. The interest in using this as a vector for vaccines has actually been around for a while now. The first mRNA flu vaccine was tested in mice in the 1990s. There's also one under exploration for rabies in 2013. Some of the early challenges with this were just delivery. mRNA itself, it quickly degrades in the body. But this started to, we began to find solutions to this with new developments in nanotechnology. One of them being lipid nanoparticles, which can encapsulate the mRNA and provide it some protection until it gets taken up by a cell. And I've got a little overview of how that, the concept of how that works. So of course, we have the spike protein on the coronavirus that's used as our antigenic component for the vaccine. We actually use an mRNA sequence that codes for that spike protein. Production is scaled up and placed in that lipid coating, which is actually the basis for the vaccine. Once it's administered into the body, the cells uptake the lipid nanoparticle, and then use the cell's machinery to actually produce that protein, which the body then recognizes as a foreign product and develops antibodies to it, leading to protection on re-exposure. And of course, we know of both the Pfizer and Moderna vaccines that use this concept widely in the U.S. now. It's hard to understate how the impact of vaccination on human disease. Here's just a snapshot of some of the decreases in cases as of 2017 and 2016, and the percent decline. And of course, with essentially eliminating smallpox and diphtheria, you can see a number of other diseases there, the decrease in incidence, as well as the more relative but still very important decreases that we have in pneumococcus, for example, with the polysaccharide vaccines. To talk a little bit more about vaccine safety and regulation. Of course, most of this occurs in the United States under the Food and Drug Administration, under the Center for Biologics Evaluation and Research, which is what allows us to have the safest and most effective vaccine supply in history. I mentioned early in the talk about some of the early events that led to Biologics Control Act, the Pure Food and Drug Act in the early part of the century. And of course, it's been a progression since that time. In 1938, the Food, Drug, and Cosmetic Act required new drugs to be shown to be safe before marketing. In 1955, the Division of Biologics Control was originally placed under the NIH. It was prompted after the incident when several children contracted polio, which was believed to be an improperly inactivated batch. Then late in the 70s, that actually transferred from the NIH to the FDA. Some other important events in 1981, the FDA and Department of Health actually revised some of the regulations around human subjects protections, including based on the Belmont report, which focused on the Tuskegee syphilis studies when a large group of African American men were studied who had known syphilis but were not told that they had syphilis, which led to a number of cases, including to congenital transmission. It's interesting to note some of the pivotal experiments and events that we think of in the history of vaccination, with children and being the first subjects and scientists testing on themselves and their family. It's only been in more recent decades that we really have the more robust human subjects protections that we think of today. But this has led to more standardized protections against, as far as institutional review boards and organizations to review research protocols, the development of new vaccines. Today, of course, we have preclinical studies that use animal models to demonstrate protection and relative safety before it's even considered in humans. And then you have, the different phases of trials, which essentially scale up, used to demonstrate, both safety and efficacy in a stepwise manner. Phase 1, when a limited number of doses are given to humans, followed by phase 2, when you give to similarly to a limited number, but with attempts to optimize the vaccine schedules and demonstrate further safety. And then with phase 3 being your larger trials to demonstrate efficacy in large numbers, which tends to be what we hear about more commonly with vaccine trials before they're marketed. And then there's, of course, post-market surveillance, which is used to detect the rare adverse events associated with vaccination and to monitor safety. In 1986, we have the National Childhood Vaccine Injury Act. This is part of what prompts healthcare providers to share the vaccine information statement that comes with all vaccines in the United States today. And that's also what introduced the vaccine adverse event reporting system, by which individuals can report adverse events. Thinking about future directions, I think mRNA vaccines, of course, we're using them in COVID-19. There's likely to be a much broader use for this technology in vaccination in the future. And I think we can look forward to that application being used in other ways in the future. There's an ongoing efforts to vaccinate against the big three: AIDS, malaria, and tuberculosis, and develop effective vaccines for all three. Of course, we have the BCG vaccination for tuberculosis, but there's always a great deal of interest in developing more widespread use of vaccine technology for that disease. For HIV too, we're still trying to gain some understanding of parts of the virus that can really provide immune protection against the virus. There's interest in a universal flu vaccine, of course, and then vaccines against some tropical diseases, malaria, we mentioned, West Nile, and dengue. Vaccines for cancers is also is in development. Of course, use of vaccines we have now as in easier to administer forms and forms that are easier to use in low resource conditions as well. So I think we still have quite a bit to look forward to in the development of vaccines in the coming years. Here's a quick summary of some of the references used today. And just to wrap up, I just included a couple of interesting photos back from the polio vaccination era. This is Salk on the cover of Time magazine. This is Elvis Presley receiving one of the early vaccinations to kind of help promote public awareness and encourage more widespread use of the vaccine. So thank you for your attention. I hope you enjoyed the talk today.